Night settles slowly over the stone courts of an ancient Greek temple. The last light has withdrawn from the columns, and the faces gathered before the altar are lit only by oil lamps and the orange breath of a newly kindled fire. A priest stands beside the flames. He raises his hands, speaks words the crowd has heard before, and waits. At first, nothing changes. The doors of the sanctuary remain closed, dark and immense, as if they belong less to a building than to the mountain itself. Then comes a sound. It is not a voice, nor the strike of a drum. It is the deep complaint of hinges beginning to turn. The temple doors move apart with no servant beside them, no visible rope, and no hand upon the bronze fittings. The opening is slow enough to feel deliberate. Firelight reaches into the chamber beyond. To the people watching, the meaning seems clear. The offering has been accepted. The god has answered. That is the surface of the story, the part designed to be seen. Beneath the floor, another story is unfolding. The altar is connected to a sealed vessel, hidden from the worshippers. As the fire warms the air inside, that air expands. It presses upon water held within the system and forces the liquid through a pipe into a hanging container. Drop by drop, the container grows heavier. Its weight pulls a cord wound around the pivots of the temple doors. The cord tightens. The doors turn. Nothing inside the machine thinks. Nothing understands the prayer. Yet each part has been arranged so that one event causes the next. Heat becomes pressure. Pressure moves water. Water creates weight. Weight pulls rope. Rope moves stone and wood. A ceremony that appears to pass from human beings to a god is, below the floor, passing through a chain of physical causes. When the fire weakens, the process reverses. The air cools and contracts. Water returns toward its first vessel. The hanging container becomes lighter. A counterweight regains control, drawing the doors shut. The miracle ends as quietly as it began, and the mechanism prepares itself to wait for another flame. Descriptions preserved in the works associated with Hero of Alexandria show that ancient engineers understood how altar fire, sealed containers, water displacement, ropes, pulleys, and weights could be combined to create automatic temple effects. Whether every detail was used in every sanctuary is impossible to know. The surviving text is not a map of all ancient temples. It is evidence that such a machine could be imagined, described, and built from materials available more than 2,000 years ago. This matters because the device is more than a hidden rope trick. A hidden assistant, pulling at the right moment, would create an illusion. Here, the visible act itself begins the mechanism. Once the fire is lit, the sequence proceeds through its own arrangement. The priest may know what will happen, but he does not need to open the doors by hand. The machine has been given a condition, and when that condition appears, it performs its task. The crowd would never see the patient preparation required before the ceremony. Vessels filled to the correct level, cords checked for tension, pivots kept free, and seals tested against leaking air. The wonder depended on precision. A small fault below could leave the god apparently unwilling to respond. Reliability, even in sacred theatre, was part of the design. Modern eyes may see only pipes and containers. Ancient eyes may have seen presence, intention, and divine approval. Between those two views lies the mystery that will guide this journey. How much of what later generations called automation had already been assembled in a world without electricity, motors, or code? And if a temple could be made to answer fire, what else had ancient engineers learned to make appear alive, every single time? The moving temple doors create an immediate, powerful temptation. It is easy to point at the hidden vessels and ropes and announce that ancient Greece had already invented the robot. Still, the closer the word robot is examined, the less simple the answer becomes. The word itself belongs to a much later age. It carries images of metal workers in factories, mechanical arms assembling vehicles, machines crossing distant planets, and human-shaped figures guided by software. A modern robot normally has a body or physical structure, a source of power, parts that create movement, a control system, and some means of receiving information from its surroundings. More advanced robots can compare conditions, alter their actions, plan a route, recognize objects, or learn from experience. The ancient temple mechanism could do none of those things in a flexible way. It could not decide whether the fire was an offering or an accident. It could not recognize the priest. It could not choose to open one door instead of another. It had one prepared relationship between one condition and one response. Heat entered the system. The arrangement converted that heat into motion. When the heat disappeared, the motion reversed. Calling it a modern robot would therefore be misleading, but dismissing it as a toy would be misleading as well. Seen one part at a time, the system contains several elements that still belong to automatic machines. The fire is an input. The heated air and displaced water carry energy through the device. The vessels, ropes, and counterweights determine how the process unfolds. The turning doors are the output. Nothing is electronic, yet the machine still moves from cause to controlled action. This is where the mystery becomes more interesting than the exaggeration. Ancient engineers were not secretly building androids in forgotten laboratories. They were discovering that behavior could be arranged inside matter. A machine did not need a mind to appear purposeful. It needed a source of energy, a carefully chosen trigger, and parts whose relationships produced the desired result. The difference between movement and behavior is small enough to be deceptive. A stone rolls downhill because gravity pulls it. No one calls the stone an automaton. But place a weight inside a designed system, control the speed of its fall, connect it to cords and axles, and use that motion to open doors at a chosen moment, and the same force begins to look organized. The intelligence is not inside the weight. It is inside the arrangement created by the builder. Modern robotics adds layers the ancient world did not possess. Sensors can measure distance, heat, pressure, light, sound, and motion. Computers can compare those measurements with stored instructions. Software can select between many possible actions. Motors can respond in fractions of a second. Some machines can adjust after mistakes. Others can operate in changing environments far beyond the narrow conditions expected by their designers. Ancient automata were usually fixed. Their rules were built into their shape. A pipe of a certain width delayed a flow. A float at a certain height opened a valve. A cord wound in one direction turned an axle forward, while another arrangement reversed it. The machine followed its construction as faithfully as a modern device follows code, but it could not step outside that construction. So the question is not whether Hero's temple doors were robots in the modern sense. They were not. The better question is how many pieces of the robotic idea were already present. Automatic action was present. Controlled energy was present. Triggered response was present. Mechanical sequencing was present. In other devices, even basic regulation would appear. That careful distinction changes the entire investigation. It allows wonder without pretending. It avoids the easy claim that history has hidden a complete technological age, while preserving the far stranger possibility that crucial ideas appeared long before the machines capable of uniting them. To follow those ideas, the story must now move away from a single temple and into the broken record of ancient technology. Some evidence survives in bronze. Some survives in copies of copies. Some survives only because a later reader decided that a difficult book of valves and cords was worth saving. Ancient machines rarely survive in the form a modern visitor hopes to find. There is no sealed workshop waiting beneath Alexandria, with rows of complete bronze servants standing in darkness. Wood decays. Rope disappears. Iron returns to rust. Bronze is melted, reshaped, and used again. What remains is scattered across different kinds of evidence, and each kind tells only part of the story. Some devices are known from technical writings. A manuscript may describe vessels, pipes, pulleys, or moving figures, sometimes with a diagram copied by a hand living centuries after the original author. Such a text can preserve an idea long after the object itself has vanished. Yet a written description also raises questions. Was the device actually built, or only proposed? Did the copyist preserve the drawing accurately? Did a translator understand the name of every part? Modern reconstruction offers another layer. Engineers and historians can follow an ancient description, build a working model, and discover whether the arrangement is mechanically possible. When the model succeeds, it proves that the text contains more than fantasy. The parts can cooperate. The water can move, the valve can open, the figure can turn. But even a successful reconstruction cannot show how many original machines existed, where they were displayed, or how often they worked without repair. archaeology provides the strongest physical evidence, though it is often the rarest. The Antikythera mechanism survived because a ship carried it to the bottom of the sea, where its broken bronze fragments escaped the furnace that may have consumed countless other devices. Its gears can be examined, measured, scanned, and compared, yet even this extraordinary object is incomplete. Much of its casing is gone. Many details must be recovered from damaged inscriptions and the relationships between surviving pieces. The history of ancient automation must therefore be assembled like a puzzle whose parts were never meant to lie beside one another. This uncertainty is not a weakness to hide. It is part of the investigation. Every claim must be placed beside its source: surviving metal, preserved instruction, later copy, modern experiment, or imaginative comparison. Only then can the documentary distinguish what ancient hands certainly made from what present minds reasonably infer. One piece belongs to Ctesibius, an Alexandrian engineer associated with pumps, water organs, and improved water clocks. Another belongs to Philo of Byzantium, whose pneumatic tradition includes an automatic female servant that dispensed wine and water after a cup was placed in its hand. Hero of Alexandria preserves descriptions of coin-operated dispensers, self-opening temple doors, singing birds, and mechanical theatres capable of carrying out prepared performances. Far from Alexandria, an unknown group of craftsmen created the geared device later recovered near Antikythera. These objects do not form a single line of robots becoming steadily more advanced. They served different worlds. One measured time, one supported ritual, one entertained an audience, one represented the cycles of the sky, one offered a drink. Their shared importance lies deeper than appearance. Each machine controlled motion. Each transformed a natural force into an intended result. Some responded to an external trigger, some regulated changing conditions. Some stored a sequence inside cords or gears. Together, they reveal a mechanical vocabulary that could be reused in many settings. The same caution must be applied to the myths that stand beside them. Talos, the bronze guardian of Crete, is not archaeological evidence. He belongs to story, yet stories reveal what a culture could imagine, fear, and desire. Long before an engineer hid pipes inside a statue, Greek poets described artificial beings that served, guarded, traveled, and killed. That may be the earliest fragment of all, not a gear or valve, but an idea. Before metal was made to move by pressure and weight, it moved in the ancient imagination. To understand why later machines were shaped like servants and divine figures, the journey must first enter the forge of a god. Before Greek engineers described valves, pipes, and falling weights, Greek storytellers imagined a workshop where lifeless material could be given purpose. It belonged to Hephaestus, the divine smith, master of fire, metal, tools, and impossible construction. His forge was not merely a place where weapons were made. It was a place where the boundary between an object and a living servant became uncertain. In the old stories, Hephaestus created objects that moved without ordinary human effort. He fashioned marvelous devices, self-moving tripods, and artificial attendants who could assist their maker. These beings were not born, they were constructed. Their abilities came from divine craftsmanship, yet the idea beneath them was strikingly practical. A made thing could carry out a task on behalf of its creator. To modern ears, such stories can sound like early science fiction, but to ancient listeners, the forge already possessed a kind of transformation that bordered on magic. Dark ore was pulled from the earth, broken, heated until it glowed, and shaped into blades, tools, armor, vessels, and human forms. Metal appeared rigid and dead when cold, then softened under flame and obeyed the hammer. Few crafts made matter seem more changeable. That may explain why the god of metalworking became the maker of artificial life. The poet did not place self-moving servants in the hands of a farmer or sailor. He placed them beside the figure whose skill turned raw substance into designed form. The forge offered a believable mythic doorway between imagination and mechanism. Yet myth must remain myth. A story about a golden attendant does not prove that ancient craftsmen built walking machines. No fragment of a mechanical woman has been recovered from a Bronze Age palace. No workshop plan explains how divine servants balanced, perceived commands, or moved their limbs. The stories reveal possibility within the imagination, not accomplished engineering. Their importance lies elsewhere. The stories taught audiences how to read mechanical wonder. When a crafted figure moved, the question was not which force drove it, but whose intention lived within it. Later engineers could exploit that habit by hiding causes inside remarkable forms. Every invention begins twice. It begins first as a desired action, and later as a workable method. Someone imagines a door that opens by itself before another person discovers how heat, water, and counterweights might open it. Someone imagines an artificial servant before pipes and valves can be hidden inside a human-shaped figure. The dream does not build the machine, but it gives the machine a role. The creations of Hephaestus performed recognizable duties. They carried, supported, served, or moved according to a purpose given by their maker. They were not simply statues that happened to stir. Their motion meant something because it completed an assigned task. This is one of the oldest ideas beneath automation. The object does not act for itself, it acts in place of someone else. There is also a quiet unease inside these tales. Crafted beings appear useful because they obey. They do not grow tired, question the command, or ask why the task must be done. But perfect obedience can become frightening when the task is violent. A servant that never refuses is comforting in a workshop and terrifying on a battlefield. Greek myth understood both sides. Artificial life could reduce labor, display unmatched skill, and extend the power of its maker. It could also become a guardian whose command was so narrow that mercy had no place within it. That guardian was Talos, the bronze figure said to circle Crete and destroy those who approached without permission. He belonged to legend, but his behavior would feel familiar to anyone living in an age of patrol drones and automatic defenses. He had a body, a territory, a task, and a hidden weakness. Long before metal truly walked, the Greeks had imagined why it might walk, and whom it might be ordered to stop. Talos appears on the edge of Crete as something neither fully alive nor comfortably lifeless. He is described as a giant made of bronze, a guardian assigned to circle the island and keep unwanted visitors away. Several times each day, he patrols the coast. When ships approach, he does not negotiate. He does not ask whether the strangers are lost, peaceful, or desperate. He follows the purpose for which he was made. The story changes across ancient sources, as myths often do. In some versions, Talos hurls stones at ships. In others, he heats his bronze body and crushes intruders against it. What remains constant is his nature as an artificial defender. He possesses enormous strength, repetitive behavior, and a command tied to a specific territory. Seen through modern language, the resemblance is unsettling. Talos has a constructed body. He follows a patrol route. He detects a boundary violation and responds with force. He appears tireless, loyal, and incapable of hesitation. These are qualities still praised in machines designed for security. They are also the qualities that make such machines dangerous when the rule they follow is too simple for the world around them. Yet Talos is not evidence of an ancient military robot. He belongs to poetry, painted pottery, and legend. His bronze body was not recovered from the soil of Crete. No engineer left measurements for his joints or instructions for his movement. The comparison is not archaeological, it is conceptual. That distinction allows the myth to reveal something more useful than a false claim. Talos shows that ancient people could imagine an artificial agent whose behavior was defined in advance. He does not choose his duty. His maker has placed the duty inside him. The guardian may appear alive, but his identity is inseparable from his command. Inside his body runs a life-giving substance, often described as ichor, held by a single vulnerable fastening near his ankle. As long as the seal remains secure, the bronze guardian continues. Once it is removed or damaged, the fluid escapes, his power fails, and the giant collapses. The image is mythic, but its structure feels mechanical. A powerful system depends upon an internal medium and a small point of failure. The body that seems invincible from the outside can be defeated by understanding what is hidden within it. Strength alone is not the secret. The secret is the arrangement that sustains the strength. His downfall carried another warning. The more mysterious a machine appeared, the more power belonged to anyone who knew its hidden structure. Knowledge could defeat what strength could not. This creates one of the oldest stories about the weakness of an artificial defender. The machine is feared by those who see only its size. It becomes vulnerable to the person who understands its design. Modern technology often produces the same reversal. A device may resist direct force, yet fail through a damaged sensor, a blocked connection, a lost signal, or a flaw in its instructions. Talos also exposes a deeper anxiety. Perfect obedience is not the same as wisdom. A wise guardian might distinguish a threat from a traveler. Talos appears to distinguish only between those permitted to approach and those who are not. His loyalty is absolute, because his world has been reduced to a rule. That is why the myth remains powerful. It asks a question that later engineers could not escape. When human beings give a machine the power to act, where does responsibility remain? Is it inside the object that carries out the command, or inside the person who decided the command should exist? The Greeks did not need gears, motors, or electronic eyes to recognize the danger. They placed the problem inside a bronze body and sent it walking around an island. But stories could move Talos, because stories require no power source. Real metal was heavier, more stubborn, and less willing to obey. To make an object act in the physical world, ancient craftsmen needed something mythology could ignore, a repeatable cause. The path from the bronze guardian to the working automaton began when wonder entered the workshop and was forced to follow the laws of water, air, weight, and motion. Myth could give bronze a soul with a single sentence. Engineering had to proceed more slowly. A storyteller could say that a guardian walked, and the listener would accept movement as part of the wonder. A builder faced harder questions. What force would lift the limb? How would that force be stored? What would begin the action, limit it, reverse it, and prepare the machine to move again? The distance between imagining artificial life and constructing automatic behavior was filled with problems that poetry never needed to solve. Greek mechanical traditions began to cross that distance by replacing divine intention with repeatable cause. A statue did not need to be awakened if a hidden pipe could make its arm move. A bird did not need breath if compressed air could pass through a whistle. A door did not need to hear prayer if heat from the altar could begin a chain of pressure, water, weight, and rotation. The outward effect could remain marvelous even after the cause became physical. This was the important change. Wonder did not disappear when engineers learned how to produce it. Wonder became something that could be designed. For the first time, a marvel could be repeated on demand. It no longer depended upon a poet's voice. It could be prepared, triggered, observed, rebuilt, and repeated. The word automaton carried the sense of something acting by itself or appearing self-moving. That appearance mattered. A visible servant turning a handle would make a device ordinary, hide the servant, replace the hand with a falling weight, and conceal the cord inside a base, and the same movement seemed to belong to the object. The audience saw action but not agency. Its mind supplied an explanation. Human beings are quick to interpret organized movement as intention. A figure that turns at the right moment seems to notice. A vessel that pours only after a cup is offered seems to respond. A mechanical bird that sings when water reaches a hidden level seems to know when its cue has arrived. None of these devices requires thought. The illusion of thought emerges because the action fits the situation. This may be the most important bridge between myth and machinery. Engineers did not first create artificial intelligence. They created conditions under which observers imagined intelligence. The machine's apparent mind existed partly in valves and cords, and partly in the expectations of those watching. Such devices could belong to several worlds at once. In a temple, they might deepen the emotional force of ritual. At a royal court, they could display wealth and command over rare knowledge. In a workshop or school, they could demonstrate the strange behavior of air, water, heat, and balance. In a theater, they could turn technical skill into narrative surprise. The categories modern people prefer, science, religion, entertainment, and illusion, were not always separated in the same way. A machine could explain nature while also making nature look supernatural. It could teach one observer and astonish another. The same hidden mechanism could be evidence of reason to the builder and evidence of divine presence to the crowd. This uncertainty gives ancient automata much of their power. They occupied the narrow space where an object moved correctly, yet the cause remained unseen. The less the audience understood the mechanism, the more intention it appeared to possess. But the machines still required a place where knowledge, materials, skilled hands, and powerful patrons could meet. That place was not the legendary forge of Hephaestus. It was a real city, crowded with ships, scholars, surveyors, craftsmen, priests, and rulers. In Alexandria, inherited Greek mathematics encountered Egyptian experience with water, construction, and measurement. Ideas moved through libraries and workshops, but so did metal, timber, glass, rope, and practical need. There, invisible forces would be turned into public demonstrations, accurate clocks, musical instruments, and self-moving displays. Myth had imagined the task. Alexandria began assembling the means. Alexandria rose beside the Mediterranean as a city of arrivals. Ships entered its harbors carrying grain, timber, metals, glass, papyrus, travelers, and ideas gathered from distant shores. Languages mixed in its streets. Merchants measured cargo. Surveyors marked land. Sailors watched the sky. Priests guarded older traditions, while scholars compared observations and copied texts. Knowledge here was certainly not suspended above ordinary life. It moved through a city that depended upon calculation. The famous library has become the strongest symbol of Alexandria, but books alone could not create machines. Around the written word stood workshops, docks, temples, palaces, construction sites, and systems for moving water. Each produced practical questions. How could a heavy load be lifted? How could a distance be measured? How could water be raised, pressure maintained, music amplified, or time divided into equal parts? These were not small concerns in a royal capital. Ships needed repair, buildings required planning, fields and gardens depended upon controlled water, armies demanded machines capable of throwing, lifting, and braking. Court ceremonies rewarded effects that made royal power seem connected to knowledge itself. A device that moved without visible hands could be useful, instructive, and politically impressive at the same time. Alexandria also stood where several traditions met. Greek geometry offered methods for describing shape, proportion, and movement. Egyptian experience surrounded the management of water, monumental building, measurement, and long observation of the heavens. Craftsmen brought knowledge that rarely appeared fully in philosophical texts: how materials behaved under pressure, where seals leaked, how wood warped, and which metal fittings endured repeated motion. It would be misleading to imagine a single room in which every famous thinker gathered to design robots. The city's mechanical culture was broader and less orderly. Ideas could pass between a written treatise and a workshop, between a courtly display and a practical pump, between a temple effect and a lesson about air. Not every connection can be traced, yet the environment made such connections possible. Here, mechanics became a way of making invisible forces visible. Air could not be seen, but its pressure could push water through a pipe. Balance could not be held in the hand, but a beam and two weights could display it. Time could not be stopped, but a steady flow could give it a moving pointer. Mathematical relationships could leave the page and enter wood, bronze, cord, and glass. That transformation is essential to the story of automation. A principle becomes far more powerful when it can be embodied. Once pressure is made to move liquid reliably, it can be used in many devices. Once a float can follow a changing water level, it can operate a valve. Therefore, the city did not need to invent the modern robot as one complete object. It needed to develop a language of dependable actions. One workshop improved a pump. Another refined a clock. A writer described a siphon. A craftsman shaped a valve that sealed more tightly. Each solution became a piece that later builders could combine. Royal support may have encouraged marvels, but necessity encouraged precision. A spectacle that failed before a ruler was an embarrassment. A clock that changed speed as its vessel emptied was useless for careful measurement. A water organ that lost pressure could not maintain its sound. Wonder depended upon control. Long before Hero recorded elaborate theatres, an earlier Alexandrian engineer confronted this problem directly. Ctesibius studied machines in which air and water had to behave predictably. His work would lead away from the dramatic image of a bronze guardian and towards something humbler, a vessel, a float, and a changing water level. Yet within that quiet arrangement lay a principle that every automatic system still requires. Energy alone is not enough. A machine must govern the force that drives it. The next step in the ancient dream was not teaching metal to walk. It was teaching water to keep time. Ctesibius enters the story without the dramatic certainty that surrounds a king or conqueror. Much about his life is uncertain, and later writers preserve only pieces of his work. Yet the machines associated with his name reveal a mind concerned with a problem that sounds simple until someone tries to solve it. How can a changing natural force be made steady? Consider a vessel with a small opening near its base. At first, when the vessel is full, the weight of the water creates stronger pressure at the outlet. The stream flows quickly. As the level falls, the pressure weakens and the stream slows. Anyone attempting to measure time by collecting that water faces an immediate difficulty. Equal moments do not produce equal amounts of flow. A rough water clock may still show that time has passed, but precision demands more. If an hour appears longer in one part of the day than another, because the vessel empties unevenly, the machine cannot become a dependable instrument. The problem is not creating movement. Water already moves. The problem is controlling its movement so that the output remains useful. Ctesibius is associated with improvements that introduced regulation into the system. Instead of allowing the working vessel to empty freely under constantly changing pressure, water could be supplied in a way that maintained a more stable level. A float rose or fell with the liquid. Connected parts then influenced the incoming flow, helping preserve the condition needed for regular measurement. This seems modest, beside a bronze giant or an opening temple. There is no human face, no sacred fire, and no audience gasping as stone doors turn. Yet the quiet float may be more important to the history of automatic control than any dramatic statue. The reason is hidden in the direction of cause. In an ordinary sequence, a force enters the machine and produces an action. In a regulating arrangement, the condition created inside the machine can influence what happens next. When the water rises too far, the float rises and restricts the supply. When the level falls, the float moves back and permits more water to enter. Change produces a response that resists further change. The machine does not know the correct level. It has no number written inside it, and no mind comparing one state with another. Its shape performs the comparison. The float's position corresponds to the water around it. The connection between float and valve turns that position into action. Modern control engineers would describe far more advanced systems with precise mathematics, electronic sensors, and rapid correction. Ctesibius did not possess that theory in its modern form. Still, the underlying desire is recognizable. A useful machine must remain stable while the world around it changes. Once the water level became dependable, new possibilities appeared. A steady flow could raise another float at a regular pace. That movement could turn a pointer, lift a small figure, mark divisions, or trigger sounds. Time, invisible and continuous, could be translated into visible stages. A robot that walks across uneven ground, a furnace that maintains temperature, and a household tank that closes its inlet at the proper height, all face different versions of the same question. How can a system respond when its condition begins to drift? The second surprise is that regulation changes the meaning of motion. A machine that merely moves may be impressive. A machine that corrects itself appears almost watchful. It seems to protect an internal order, even though that order exists only because the builder arranged matter to behave in a certain way. Ctesibius did more than improve timekeeping. The mechanical traditions linked to him include pumps and the water organ, devices that required careful use of air and liquid. Across them, pressure had to be created, preserved, released, and converted into a useful result. Those principles would become a vocabulary. Floats could act upon levers. Siphons could begin flow when a hidden level was reached. Compressed air could move water or produce sound. Counterweights could return parts to their starting position. The ancient machine was learning not one trick, but a set of reusable words. From those words, later engineers would write more elaborate mechanical sentences. Once water could be regulated, ancient engineers possessed more than a solution for clocks. They possessed a set of mechanical relationships that could be carried from one device to another. Water, air, weight, and balance became a language. Each element had its own behavior, and skilled builders learned how to combine those behaviors into controlled results. A siphon was one useful word in that language. Water could rise within a curved tube and then continue flowing after it passed a certain height. To an observer who could not see the hidden pipe, the sudden movement might seem mysterious. To the engineer, the height of the water served as a trigger. Before the level was reached, nothing happened. Afterward, the vessel emptied. A float offered another kind of control. Because it followed the surface of a liquid, its position could represent a changing condition. Attach it to a lever, and rising water could open or close a passage. Attach its motion to a pointer, and an invisible process became visible. The float needed no sight. Contact with the water was enough. A sealed container allowed air to become an active force. Heating the air increased pressure. Pouring liquid into one chamber could compress the air inside and drive water from another opening. A stream that appeared to move by itself was often being pushed by pressure that the audience could neither see nor easily imagine. Weights and counterweights gave machines stored movement. A raised weight contained the possibility of falling. When connected to a cord, axle, or pulley, that fall could turn, lift, or pull another part. A counterweight could reverse the action or return the mechanism to its beginning. What gravity did naturally could be delayed and directed. These principles appeared in devices associated with Ctesibius. A force pump used controlled movement to draw in and expel water. The hydraulis, or water organ, used water and air to help maintain pressure for musical sound. The outcome was different from a clock, yet the internal concern was similar. Create a force, regulate it, and turn it into an effect that could be repeated. This is why ancient automata should not be viewed as isolated miracles. They grew from a toolkit. A builder did not need to invent motion from nothing each time. He could choose a vessel, a pipe, a float, a valve, a weight, or a cord, then arrange them according to the task. Modern engineers work with components whose names sound different: sensors, controllers, motors, processors, and power supplies. The ancient equivalents were far less flexible, but the habit of system building was already present. One part received a condition, another transmitted force, another limited or delayed the action. A final part produced the movement seen by the audience. The most important work was often hidden. A painted bird might draw attention, but the pipe beneath it determined when it sang. A moving figure might seem alive, but the size of a vessel controlled the timing. A door might appear obedient to ritual, but a counterweight prepared its return. The machine's visible form told a story. Its invisible parts enforced a rule. That distinction prepares the next stage of the journey. Regulation must now be examined more closely, because it reveals how a physical system can react to itself. Before a machine could convincingly serve a human being, it had to become dependable enough to maintain order within its own body. The path therefore turns again toward the water clock. A single drop enters, the level rises, and a float begins to move. Nothing in the vessel is alive, yet the arrangement can observe change, carry that change through a linkage, and alter what happens next. Soon, those same principles will be hidden inside the shape of a servant. But first, the quiet machinery must show how matter can follow a rule without anyone standing nearby to enforce it. Nature offers power freely, but rarely in the form a machine would prefer. Water surges, slows, leaks, and changes pressure as its level falls. Air expands with warmth and contracts with cold. Rope stretches, wood swells, metal fittings wear against one another. Friction steals motion a little at a time. A device may work perfectly once and fail on the next attempt because the forces driving it are never completely obedient. This was the hidden enemy of ancient automation. Producing movement was not enough. The movement had to arrive at the correct time, continue at a useful rate, and stop before the mechanism damaged itself. A machine that opened a temple door too early, poured too much wine, or allowed a clock to run unevenly, would break the illusion of purpose. The water clock makes the problem easy to see. Imagine following a single drop as it leaves one vessel and enters another. The drop has no knowledge of time, it simply falls. Yet thousands of such drops, moving at a controlled rate, can raise a float. The float can lift a rod. The rod can move a pointer past marks that divide the day. Continuous flow becomes ordered information. If the flow changes, the meaning changes with it. A faster stream makes time appear to hurry. A slower stream makes it appear to linger. For the clock to become trustworthy, the machine must protect its own rhythm from the changing pressure inside the vessel. One method is simple in appearance. Water enters a regulating chamber. A float rests upon its surface. As the level rises, the float moves upward and influences a valve or inlet. The supply is reduced. If the level begins to fall, the float descends and the passage opens farther. The changing condition inside the chamber affects the flow entering it. This differs from a sequence that simply runs forward. Light a fire, and expanding air pushes water. Release a weight, and gravity pulls a cord. These actions proceed without checking their result. A regulating system allows the result to shape the next action. The system is not conscious, but it is no longer merely passive. The distinction can be expressed without modern technical language. One machine obeys a command and continues. Another also feels the condition it has created. The word feels is only a metaphor. The float has no sensation. Its position changes because water supports it. Yet that physical position carries information. High water places the float here. Low water places it there. A connection turns the difference between those positions into a change at the inlet. This is the quiet foundation of feedback. Modern systems use electronic sensors, measured values, and controllers that calculate correction. Ancient regulators used direct contact, leverage, and balance. Their methods differ greatly, but both confront the same truth. Force must sometimes be adjusted while being used. The first surprise is that self-correction does not require thought. A machine can oppose a change without understanding why the change matters. The rule exists in the relationship between its parts. The second surprise is that such a device can appear protective. It preserves a level, maintains a rhythm, and prevents the system from drifting too far. To an observer, this steadiness can resemble intention, though no intention exists within the mechanism. Once that idea is understood, the ancient float becomes more than an object riding upon water. It becomes an observer made of matter, a messenger connected to a lever, and a controller that alters the flow. Three roles are contained in one moving piece. The next step is to look more closely at that movement. How can position become a signal? How can a simple object represent the condition around it? And how can a builder turn that representation into action? Inside the answer lies a principle that would later shape machines far more complex than any Alexandrian clock. The float rests where two worlds meet. Part of it sits above the surface, visible and dry. Part of it is held by the water below. It does nothing dramatic. It makes no sound and produces no light. Yet as the liquid changes, the float follows with perfect simplicity. When water enters the chamber, the surface rises. The float rises with it. When water leaves, the surface falls and the float descends. Its position is therefore not random. At every moment, it corresponds to the condition inside the vessel. That correspondence is a form of information. The float does not contain a written number. It does not measure the depth with marks or announce a result. Still, anyone looking at its height could infer whether the chamber was nearly empty or nearly full. Connect the float to another part, and the machine itself can use the same difference. A rod may rise with the float. A lever may pivot. A valve may narrow the opening through which fresh water enters. The chain is direct. Higher water places the float higher. The higher float moves the lever farther. The lever restricts the inlet. As the level begins to fall, the relationships reverse, and the inlet opens again. No separate messenger carries instructions from the chamber to the valve. The linkage is the message. Matter responds to matter. Calling the float a sensor can be helpful, but the comparison must remain careful. It does not create an electrical reading. It cannot send its information to several machines or store a history of past levels. It reacts only through the connection built around it. Its intelligence is zero. Its usefulness is real. A familiar descendant survives in ordinary places. Inside many water tanks, a float rises until it closes an inlet. When water is used, the float drops and the supply begins again. The device is so common that it attracts little wonder, yet its calm repetition contains the same basic idea that made ancient regulation possible. The surprising part is not the float itself, it is the realization that a rule can be built into shape. No instruction needs to be spoken each time the water changes. The builder has already placed the instruction into lengths, pivots, angles, and limits. The machine follows the rule because its parts have nowhere else to go. This is physical information processing in its simplest form. One state of the world produces one position. That position produces one mechanical response. The response alters the state of the world. A circle begins to appear. Water changes the float. The float changes the valve. The valve changes the water. Cause travels around the loop, returning to the condition from which it began. If the parts are proportioned correctly, the loop settles near the level the builder intended. If they are badly designed, the water may rise too far, fall too low, or swing repeatedly between extremes. Ancient engineers may not have described this with modern equations, but successful construction demanded observation. A lever that was too short would not close the passage. A float that was too heavy might respond poorly. A valve that leaked would defeat the correction. The rule had to be discovered through material, not merely imagined. This reveals why working automata required patient craft. The grand effect visible to an audience depended upon small relationships hidden inside the device. A fraction of movement at a float could decide whether a clock kept steady time or slowly lost it. Once position could carry information, almost any changing condition might become a trigger. A descending cup could open a passage. A rising water level could begin a siphon. A rotating drum could release one cord and tighten another. Instructions did not need ink or symbols. They could exist as paths through which matter was forced to move. That insight leads beyond the water chamber. A complete automatic system needs energy, a means of control, a path for transmitting force, and an action that appears at the end. In the next step, these pieces will be gathered into one architecture. Only then will it become clear how a silent arrangement of ordinary materials could imitate purposeful behavior. An automatic machine begins with energy. Without energy, every valve, lever, and cord remains still. Ancient builders drew that energy from familiar sources: water held above a lower level, air compressed inside a sealed vessel, heat expanding beneath an altar, or a weight raised and left waiting for release. Energy alone, however, produces only uncontrolled change. Water spills, air escapes, heat spreads. A weight falls. To turn any of these events into useful motion, the machine needs control. Control may appear as a narrow opening that slows a stream. It may be a float that closes a valve, a peg that catches a cord, a knot that reaches an axle at a chosen moment, or the carefully measured length of a pipe. These parts do not provide the main force. They decide when, where, and how that force is allowed to act. Next comes transmission. A cord carries the pull of a falling weight to a distant figure. A pulley changes the direction of the pull. An axle converts the pull into rotation. A lever enlarges a small movement or transfers it across the interior of a statue. The machine becomes a path through which force travels. At the end of the path appears the action visible to the audience. A pointer rises. A bird turns. A door opens. A servant lowers her hand. The visible movement may be graceful, sacred, or human in form, but it remains the final result of energy passing through control and transmission. None of the parts looks like a robot by itself. A weight is only a weight. A pipe is only a hollow passage. A lever is only a beam that pivots. Their importance emerges when they are arranged to cooperate. This is the ancient architecture of automatic behavior: power, control, transmission, and action. Modern machines divide these roles differently. Electricity may power motors. Sensors may provide measurements. Software may choose between several actions. Yet the older systems reveal the same need to separate raw force from organized performance. The machine must not merely move, It must move in the way intended by its maker. A falling weight becomes something like a motor only when its descent is governed. If it drops instantly, it provides one violent pull and then stops. If cords, drums, friction, and gearing slow the fall, the same weight can produce a sequence lasting long enough to animate a performance. Likewise, any statue truly becomes an automaton only when the machinery inside gives its movement order. The human shape is not the source of the behavior. It is the mask through which the behavior is interpreted. This distinction matters because ancient automation was not built around a mechanical brain. It was built around controlled energy. Builders learned how to delay motion, release it, divide it, reverse it, and prepare it to occur again. Those abilities could create a machine that seemed patient, responsive, or obedient. The more perfectly the visible action matched the surrounding situation, the more purposeful it appeared. A figure pouring at random would look broken. A figure pouring only after a guest offered a cup would seem attentive. The difference lay not in intelligence, but in the trigger. That trigger could come from a human body. The weight of a vessel placed in an extended hand could lower an arm, open an air passage, and begin a timed release of liquids hidden within the figure. One physical gesture would enter the machine and return as service. The next device brings every principle together. It has a human form, stored material, a contact input, a mechanical controller, and a visible response. It cannot see the guest or understand the request. Yet for a few carefully arranged moments, it behaves exactly as a servant should. In the writings linked to Philo of Byzantium, the ancient dream steps down from the divine forge and stands beside a dining cup. Philo of Byzantium survives less as a complete biography than as a name attached to a technical tradition. He belonged to the Hellenistic world of engineers, who studied fortification, artillery, mechanics, and the strange powers of air and water. Much of what was once written has been lost, altered, or preserved through later languages. The path from his workshop to the present is therefore not a straight road. It is a chain of copying, translation, interpretation, and reconstruction. That fragile survival matters. A technical manuscript depends upon more than words. A damaged poem may still be understood when several lines are missing. A damaged machine description can become useless if a single pipe is drawn on the wrong side of a vessel. Measurements, connections, and hidden passages carry the meaning. When copyists misunderstood them, the machine itself could disappear from the page. Among the devices linked to Philo's pneumatic tradition is an automatic servant shaped like a young woman. She stands holding a jug in one hand, while the other extends outward to receive a drinking cup. Inside her body are vessels containing wine and water, along with pipes and passages that regulate the flow. The figure is striking because the human shape is unnecessary. The same reservoirs and valves could have been hidden inside a chest or column. The machine would still pour. But a box releasing liquid is a dispenser. A woman-shaped figure lowering her hand and filling a cup appears to serve. The body changes the story. At an ancient banquet, service carried familiar gestures. A cup was offered, a servant approached, wine was poured and commonly mixed with water. Philo's device turned this social sequence into a mechanical one. The guest did not need to find a tap or lift a lid. He interacted with a figure whose pose already explained what to do. Modern reconstructions help reveal how the arrangement may have worked. They show that the description is not merely a fantasy about an animated statue. A cup placed in the extended hand can supply enough weight to move a linkage. That movement can open passages connected to the hidden liquids. As the operation proceeds, the machine can release wine and then water in an ordered response. The phrase "first robot" is often attached to this device because it attracts attention. The label is understandable, but it must be handled carefully. The servant cannot walk through a room, recognize a person, hear a command, or change its task. It possesses no intelligence and no freedom beyond the narrow action built into it. What the surviving design securely demonstrates is still remarkable. An anthropomorphic machine could be activated by physical interaction and could perform a prepared service through hidden control. The first mystery lies in its appearance. Why give the mechanism a face and body when those features do not improve the flow of liquid? Perhaps the human form made the action easier to understand. Perhaps it increased wonder. Perhaps Perhaps it allowed a technical demonstration to become an encounter. The second mystery lies in the lost context. Was the device built for a court, a banquet, a teaching display, or a writer's collection of ingenious possibilities? The text preserves the mechanism more clearly than the room in which it may have stood. That uncertainty should not reduce the achievement. The machine joins function with theatre. It responds through contact. It uses stored material, pressure, passages, and movement. It transforms the weight of an ordinary cup into an instruction. The most important moment lasts only an instant. A guest approaches the silent figure and places the vessel into her waiting hand. The arm begins to descend. For the watching guest, however, the machine seems to recognize the request. Nothing in the servant knows that hospitality has begun. Yet inside the body, one carefully prepared condition has been met, and the hidden sequence is ready to unfold. The guest sees a figure holding a jug. Her free hand is extended, palm upward, waiting. Nothing moves until a cup is placed upon it. The vessel may be small, but its weight is enough to change the balance inside the statue. The hand descends slightly. That movement is the beginning of the command. A connection hidden within the arm shifts with it. A rod, cord, or passage linked to the motion changes position. Air that had been trapped is allowed to move, or an opening that had been closed is uncovered. Wine begins to leave a reservoir concealed inside the body and travels through the jug into the cup. To the guest, the servant appears to respond. The cup has been offered, and the figure pours. The action matches the social moment so well that the mechanism almost disappears behind the gesture. Inside, nothing is social. There is only weight, balance, pressure, and flow. As wine enters the cup, the load in the servant's hand increases. The hand may descend farther, carrying the mechanism into another stage. A second passage opens, allowing water to flow from a separate vessel. The order matters. Greek wine was commonly mixed, and the machine reproduces that expected practice. It does not simply release two liquids at random. It performs a prepared sequence. The cup is therefore both request and control. Its first weight begins the action. Its increasing weight helps advance the mechanism. The guest does not press a marked button, yet the operation is interactive. Human contact changes the state of the machine. This is the first major surprise. The servant does not see the cup, but it detects a condition created by the cup. Weight becomes information. Still, the second surprise is that the response contains stages. One input does not merely open one tap. The arrangement can coordinate separate reservoirs and release them in an intended order. The machine behaves according to a small chain of conditions. When the cup is removed, the hand becomes lighter. A counterweight or balancing arrangement can return it toward the original position. The passages close. The flow stops. The servant resets, waiting for another vessel. The full operation can be described as a conversation without language. The guest places the cup. The machine answers with movement. The changing load carries the exchange forward. Removal ends it. No mind understands either side, but the pattern resembles request, service, and completion. This resemblance explains why the human form is so powerful. A plain container responding to weight would seem clever. A female attendant doing the same thing appears attentive. The face, posture, and jug encourage the observer to interpret mechanical causation as social behavior. Yet the illusion has strict limits. Place another object of suitable weight in the hand, and the same sequence may begin. The servant cannot know whether it holds a cup, a stone, or a piece of metal. It responds only to the physical condition for which it was designed. That limitation reveals the difference between recognition and activation. A modern robot may use cameras and software to identify an object before acting. Philo's device requires no identification. The user arranges the world so that the correct trigger is presented. This does not make the machine trivial. Many automatic systems still depend upon carefully defined inputs. A door opens when a sensor detects presence. A dispenser releases material when a lever is pressed. The intelligence may belong more to the design of the interaction than to the device itself. Philo's servant embodies that design with unusual elegance. The human guest knows what to do because the statue's hand is waiting. The machine knows nothing, yet its form guides the person toward the one action that will make it appear responsive. For a few moments, mechanism and expectation fit together perfectly. Input becomes control. Stored liquid becomes output. Balance becomes timing. A social ritual is translated into physical law. The question now becomes unavoidable. If a machine has a body, receives an input, controls stored material, and produces an ordered action, how far is it from a robot? The answer depends not only on what the servant can do, but on everything it cannot. Placed beside a modern robot, Philo's servant seems both familiar and impossibly distant. The comparison works only when each part is examined, without forcing the ancient machine to become something it was not. The cup provides the input. Its weight changes the position of the hand. That movement influences the hidden passages. Pressure and gravity move the liquids. The jug directs them into the vessel below. A counterweight, or balancing system, helps return the machine to its beginning. In modern terms, the hand can be compared with a basic contact sensor. The linked passages and valves resemble a controller because they determine which liquid moves and when. The stored wine and water provide material for the task, while pressure and weight supply the force. The pouring is the visible action. These similarities are real, but narrow. The servant cannot identify the guest. It cannot decide whether the person has already received enough. It cannot change the mixture, refuse an unsuitable object, or correct a spill. It cannot learn that one cup is heavier than another. It has no model of the world beyond the single physical relationship built into its body. A stone placed in the hand could activate it. That fact breaks the strongest illusion. The machine does not understand hospitality. It responds because the environment has met a mechanical condition. Yet this limitation also reveals the intelligence of the design. The builder does not attempt to make the servant understand every possible object. Instead, the human setting is arranged so that the correct interaction is likely. A guest sees an open hand and offers a cup. The form guides behavior. The user supplies part of the order that the machine itself lacks. Modern machines often depend upon the same principle. A button, slot, handle, or marked surface teaches the user how to produce a valid input. The system may appear effortless because its designers have reduced the number of actions that can occur. Philo's servant, therefore, belongs neither among statues nor among modern autonomous robots. It is an ancestor of interactive automatic machinery. It joins human form with a trigger, a control arrangement, stored contents, and a reset. Its response is fixed, but it is organized. Its action is limited, but it is conditional. The device becomes less robot-like when its intelligence is examined, and more robot-like when its architecture is examined. That is the central twist. The face promises awareness that is not present. The mechanism delivers structured interaction that a simple toy does not possess. Both impressions must be held at once. This balance protects the documentary from two easy mistakes. The first is to announce that ancient engineers built robots equal to modern machines. They did not. The second is to assume that anything lacking electronics and software has no place in the history of robotics. That conclusion ignores the development of control, sensing, sequencing, and actuation. Robotics did not arrive in one moment. Its parts appeared separately. One device regulated water, another responded to weight, another stored a performance in chord, another embodied astronomical calculation in gears. Centuries later, new materials and new forms of power would bring those functions together. The servant's greatest importance may therefore lie in the encounter it creates. A human being performs an ordinary gesture, and an object answers in the expected way. For a moment, the line between tool and agent becomes uncertain. That uncertainty would become even stronger in sacred space. Hero of Alexandria described machines that linked coins to measured water, altar fires to opening doors, and hidden pressure to signs of divine response. These devices did not serve one guest. They shaped the experience of entire crowds. The banquet room now recedes. The cup is lifted from the servant's hand, the passages close, and the figure returns to stillness. Ahead waits a temple where the machine's outer form is not merely human. It is miraculous. A worshipper approaches a small device near a sacred place. It does not resemble a modern vending machine. There is no glowing display, no row of choices, and no mechanical hum. There is only a vessel, a narrow opening, and a slot prepared to receive a coin. The coin falls onto a small plate attached to a balance. Its weight lowers the plate. The movement pulls or lifts a connection that opens a valve. For a brief moment, sacred water flows from the container. Then the coin slides away, the balance returns, and the passage closes. The entire exchange lasts only seconds. Hero of Alexandria describes a coin-operated liquid dispenser in his work on pneumatics. It is often introduced as the first vending machine, a title that makes the ancient device sound surprisingly modern. The comparison is useful, but the mechanism deserves attention beyond the label. A standardized object enters the system. Its accepted weight produces a controlled movement. That movement releases a measured service. The user does not reach inside the container or depend upon an attendant to judge the amount. Payment and operation are joined physically. The design solves more than one problem. It connects access to the deposited coin, and it limits the quantity of liquid released. Without such control, a visitor might take more than intended, or require someone to supervise every use. The mechanism replaces repeated human judgment with a fixed rule. Insert the coin, and the rule begins. For late visitors, the device may have seemed almost impartial, giving the same measured answer without fatigue, favor, argument, or the need for persuasion at all. The machine does not know the coin's value. It cannot read an image stamped upon the metal. A different object of similar weight and shape might produce the same response. Once again, activation is not recognition. The system accepts a physical condition, not a social meaning. Yet the social meaning is supplied by the setting. The worshipper understands that the coin is an offering or payment. The machine turns that custom into movement. To the user, the exchange has order. Something is given, and something is received. This principle remains familiar. A coin, token, card, or signal authorizes a prepared result. The technology has changed, but the pattern persists because it is efficient. The machine stands between a resource and the person requesting it, enforcing the same condition each time. There is no evidence that ancient cities were filled with commercial vending devices. Hero's description proves the concept, not the scale of its use. The machine may have been built in limited settings, demonstrated to students, or preserved because it was ingenious rather than common. The honest mystery is not how widespread it was, but why someone thought to connect payment and automatic release at all. The answer may lie in the Alexandrian habit of turning relationships into mechanisms. Weight could represent value. Balance could enforce a limit. A valve could deliver the result. Social order became physical order. This small dispenser also shows that ancient automation was not confined to theatrical marvels. A device could perform an administrative task. It could measure, restrict, and repeat. The effect was less dramatic than a moving statue, but perhaps more practical. Still, Hero understood that the same hidden forces could produce far greater wonder. A coin could open a small valve. Fire could move water into a hanging vessel. A hanging vessel could pull ropes around massive pivots. The difference between a measured stream and a divine entrance was one of scale and arrangement. The worshipper receives the water and steps away. Behind the simple action lies a rule made from metal and balance. Ahead, the documentary returns to the temple doors from the opening scene, now prepared to follow every invisible movement beneath the floor. There, automation will no longer manage a small quantity of liquid. It will manage anticipation itself. Return now to the temple after sunset. The altar burns before the closed doors, and the crowd waits between ritual and response. From above, the event appears simple. The priest lights the fire. Time passes. The sanctuary opens. Below the stone floor, the sequence begins with air. A sealed vessel is connected to the altar, or placed where the heat can reach it. As the fire grows, the air trapped inside becomes warmer and expands. Because the vessel is closed, the expanding air cannot simply drift away. It presses against water held within the system. The pressure forces that water through a connecting pipe into another container. This second vessel may hang from a cord. At first it is light. As water enters, it grows heavier. The added weight draws the cord downward. The cord is wound around the pivots or axles connected to the temple doors. Its downward pull produces rotation. The doors begin to turn. The action is not immediate, and that delay is important. Heat must build, air must expand, water must travel. The hanging vessel must gain enough weight to overcome resistance. Only then do the doors move. The crowd experiences a pause between offering and answer, a silence in which expectation can deepen. If the doors opened at the instant the flame appeared, a direct connection might feel obvious. Because the response is delayed, it seems considered. The temple appears to wait. The machine does not wait. It accumulates. That difference lies beneath the entire illusion. The delay is not evidence of thought, but the time required for physical changes to reach a threshold. Yet to human observers, a delayed response often feels more intentional than an immediate one. The interval allows emotion to enter the mechanism. As the fire continues, the doors reach their open position. The sanctuary beyond becomes visible. The machine has transformed heat into pressure, pressure into moving water into weight, and weight into rotation. No single part performs the miracle. The effect belongs to the chain. When the ceremony ends and the fire weakens, the air cools. Cooling air contracts, reducing the pressure that forced the water outward. The liquid can return toward its original vessel. The hanging container becomes lighter. A counterweight, previously overcome, now pulls the system in the opposite direction. The doors close. The reversal gives the machine a complete cycle. It does not merely spend its energy and remain useless. Under the right arrangement, it returns toward the condition from which another ceremony can begin. Hero's written description demonstrates the mechanical possibility of such an automatic entrance. It does not tell historians exactly how many temples used it, which crowds witnessed it, or whether every installation followed one identical plan. Reconstructions can show that the principles work, but they cannot restore the entire social world around the device. That uncertainty should remain visible. It protects the story from becoming a claim that every ancient priest relied upon hidden machinery. Temples contained many forms of ritual, architecture, music, scent, procession, and performance. An automaton would have been one possible instrument among them, not an explanation for religion itself. Still, the mechanism reveals extraordinary understanding. The builder had to anticipate heat, pressure, water volume, friction, rope tension, door weight, and the strength of the counterbalance. A weak seal could ruin the effect. Too little water would fail to pull the doors. Too much force could damage the pivots. The divine appearance depended upon earthly precision. This is the chapter's deeper reveal. The machine did not only control stone and wood, it controlled timing, and timing shaped belief. The audience saw fire, waited, and received movement at the emotionally strongest moment. Whoever understood the system possessed two kinds of knowledge. One concerned pressure and balance. The other concerned people. That does not prove deliberate fraud. The same device could be sacred theater, technical demonstration, royal spectacle, or all three at once. But it shows that ancient engineers understood something modern designers still use. Hidden systems become most powerful when their actions fit the expectations of the people watching. The doors stand open. The mechanism rests under the floor. Above it, wonder has already formed its own explanation. Wonder begins where explanation disappears. An ancient observer could see water flow, hear a bird sing, or watch a door open, yet remain unable to identify the force responsible. Air was invisible. Pressure had no shape. A siphon could begin suddenly after a vessel reached a hidden level. The result appeared before the cause could be understood. Greek writers used ideas connected with astonishment to describe such experiences. The purpose of an automaton was not always to perform useful labor. Sometimes its value lay in making familiar materials behave in an unfamiliar way. Temples and ceremonies offered ideal settings for that moment. Ritual already directed attention. Architecture separated sacred space from everyday space. Music, flame, scent, procession, and spoken words prepared the crowd to expect meaning. If a mechanical effect appeared within that sequence, it did not arrive as an isolated trick. It arrived inside a story the audience already understood. A door opening after an offering could appear to confirm acceptance. A figure pouring liquid might seem obedient to an unseen power. Mechanical birds singing near a sacred image could make the environment feel responsive. The device did not need to explain itself. Its silence allowed belief, curiosity, and fear to fill the gap. It would be too simple to call every such effect deception. Ancient engineers, priests, rulers, teachers, and spectators did not necessarily divide religion, science, entertainment, and technical display as modern categories do. A mechanism might demonstrate the power of air to one viewer, enhance ritual for another, and display the wealth of a patron to someone else. The same object could hold several meanings at once. Still, concealment was central to its power. If the pipes, weights, and assistants were fully visible, attention would move from the effect to the process. Hiding the mechanism allowed the machine to appear unified. Instead of seeing 10 separate causes, the audience saw one purposeful action. Modern technology often follows the same design. A robot's casing hides wires, processors, motors, sensors, and joints. A user sees one machine rather than thousands of components. The outer form creates a character. The inner complexity becomes invisible unless something fails. In ancient automata, concealment did more than improve appearance. It controlled interpretation. The person who knew the hidden arrangement understood pressure and balance. The person who did not might explain the movement through divine presence, magic, or living agency. Knowledge therefore produced social power. Whoever controlled the mechanism could influence not only what happened, but what others believed had happened. This does not require a conspiracy. Every performance depends upon unequal knowledge. The builder knows where the cord is tied. The audience does not. The storyteller knows when the reveal will arrive. The listener waits. The difference creates suspense. Ancient mechanical wonder operated through the same psychological distance. The machine did something correct at the correct moment, while its true cause remained beyond sight. The first reveal is that hidden machinery was not merely a practical necessity, it was part of the experience. The machine became more convincing as its explanation became less accessible. The second is that automation could organize a crowd's emotions as carefully as it organized motion. It delayed, surprised, answered, and returned to stillness. Its sequence guided attention. Hero's greatest devices extended this control beyond a single effect. Instead of opening one door or releasing one stream, they coordinated figures, scenery, sounds, and timed actions into complete mechanical stories. Once started, the performance could continue without visible operators. The temple therefore leads naturally to the theater. Both depend upon expectation, concealment, and carefully arranged time. But in the theater, the machine does not merely answer a ritual, it tells a narrative. Behind the painted stage, cords are wound around drums. A weight waits above the floor. Every future movement has already been placed into the path the mechanism will follow. When the weight is released, the story begins. A small theater stands before the audience, compact enough to seem like a shrine, a cabinet, or a carefully decorated stage. Its doors are closed. Painted figures wait behind them. No actor breathes inside. No visible servant holds a rope. Yet once the device is released, the performance begins. The doors open, figures move across the scene, elements of the setting change. A sound arrives at the chosen moment. One action follows another, with enough order to create not merely motion, but a story. Hero of Alexandria's work on automata describes mechanical theaters in both mobile and stationary forms. These were not full buildings filled with human performers. They were engineered displays whose figures, scenery, sounds, and movements could be coordinated by hidden mechanisms. The distinction matters. A statue that raises one arm demonstrates a single effect. A theater must control several effects and place them in sequence. It needs a beginning, development, and ending. Timing becomes as important as movement. From the audience's side, the device appears to proceed alone. Once activated, it no longer requires an operator to step forward and pull each cord separately. The machine carries the performance through a prepared order. This gives the display a peculiar authority. It seems to remember what comes next. It remembers nothing. The spectators could not pause the sequence or ask it to change. Once released, the mechanism carried them toward an ending prepared long before they entered the room that evening. The future of the performance has already been built into the arrangement behind the stage. A raised weight stores energy. Cords wrap around drums or axles. Pegs, attachments, and changes in direction determine when parts move and which way they turn. The machine does not invent the story as it performs. It follows a path chosen earlier by the builder. Heroes' descriptions are valuable because they preserve more than praise for a marvelous object. They attempt to explain how the effect can be made. The reader enters a technical world of measurements, chords, wheels, vessels, and timing. The marvel is opened, at least partly, for inspection. Modern reconstructions and scholarly studies have tested these principles, asking whether the sequences described could function in practice. The answer is not that every detail is certain. Manuscripts change through copying, and ancient craftsmanship cannot be recovered completely. Still, the underlying systems can produce coordinated movement. The first major reveal is that the theatre is an automatic narrative. It does not only imitate a living creature, it arranges events in time. The second is that the machine's most important achievement is almost invisible. The audience notices the figure that turns or the door that opens. The builder must think about the delay before that movement, the force required, the return of another part, and the possibility that one action could interfere with the next. Every chord length matters. Every knot contains timing. Every axle must rotate far enough, but not too far. If the weight descends too quickly, the story rushes. If friction steals too much force, a figure stops before its cue. The emotional rhythm depends upon mechanical discipline. The theatre therefore joins engineering with storytelling. A narrator guides attention through words. Hero's machine guides it through motion. Both depend upon withholding, release, and expectation. For late-night listeners, the image is strangely peaceful. Somewhere inside the cabinet, a weight descends with patient certainty. Chords tighten and loosen. Painted figures obey paths they cannot leave. The audience watches a world whose future has already been decided. But how was that future stored? Not in a written script read during the performance, not in a human memory. The order existed in the way chords had been wound before the doors opened. To understand the closest ancient approach to programming, the documentary must now move behind the painted scene. There, the story is no longer made of characters. It is made of rope. Behind the stage, the machine's future begins with a suspended weight. The weight is raised before the performance and connected to a cord. When released, gravity draws it downward. The falling mass pulls the cord, and the cord turns an axle or drum. That sounds like a single motion, but the cord can be arranged to produce far more. If it is wound around a drum in one direction, the rotation may move a figure forward. If the winding changes direction, the same continued pull can reverse the rotation. A cord may tighten one linkage, then release it. A peg may catch another line at a prepared point. Separate cords may control doors, wheels, figures, or sound-making devices. The sequence exists in geometry. Length determines duration. Direction determines movement. Attachment determines which part responds. The position of a knot or peg determines when a new action begins. Before the audience arrives, the builder has already made every important decision. He has wound the cord, placed the connections, raised the weight, and tested the path. When the machine starts, it does not receive new instructions. It physically follows the arrangement prepared in advance. This is why the cord can be compared with a stored program. The comparison must remain limited. A modern program is symbolic information that can be copied, edited, transmitted, and executed by many compatible machines. Hero's cord is part of the mechanism itself. It cannot be separated easily from the physical device, and it cannot command actions the theatre was never built to perform. Yet the resemblance remains clear. Change the winding, and the behavior changes. Alter a connection, and one figure moves earlier or later. Reverse part of the path, and motion reverses. The builder can revise the sequence without creating every component again. The distinction is incomplete, because hardware and instruction remain tangled together. The cord both stores the order and transmits the force that carries it out. That is the chapter's central surprise. Instructions do not have to exist as words, numbers, or electronic code. They can exist as physical constraints. A groove guides a wheel. A peg releases a catch. A knot reaches a point and changes tension. Matter can be shaped so that only one future unfolds. The process also resembles the work of constructing an algorithm in another sense. The builder must break a desired performance into smaller steps. First open the doors, then move the figure, delay the sound, reverse the platform, stop one action before the next begins. The story must be translated into operations. If the performance fails, the builder does not ask whether the machine misunderstood the drama. He looks for the physical cause. The cord may be too short, friction may be too great, a peg may release too early. The sequence is revised through testing. This iterative process brings ancient mechanics surprisingly close to a modern habit of programming. Imagine an outcome, divide it into instructions, run the system, observe the failure, and adjust the instructions. Still, Hero's theatre has no ability to examine its own performance. It cannot detect that a figure has become stuck or that a door failed to open. The weight continues to descend. Later actions may proceed even when earlier ones have gone wrong. The program is fixed and blind. That blindness gives the performance a dreamlike quality. Every figure obeys, whether or not the scene remains sensible. The machine follows necessity, not understanding. A human operator could stop it. The device itself could not choose. This limit is important because it separates mechanical sequencing from intelligence. The theatre stores order, but not judgment. It can reproduce a story, but cannot interpret one. It can change behavior only when a builder rewinds or reroutes the chords. Even so, reconfiguration raises a final question. If the same machine can perform differently after its chord arrangement is changed, does that make it programmable? The answer depends upon how strictly the word is used. The next section will test that boundary. It will also reveal why theatre, rather than labor, may have pushed ancient automation toward its most complex sequences. A story demands more than repetition. It demands time, surprise, reversal, and an ending. The word programmable creates an image of screens, keyboards, and lines of code. Hero's theatre possessed none of these things. Its instructions were not symbols interpreted by a general machine. They were physical arrangements, embedded in chords, pegs, drums, and attachments. Even so, the theatre could be changed. A chord rewound in another direction could reverse movement. A different length could alter timing. An attachment shifted to another point could cause a figure to begin earlier or later. The machine's range remained limited by its construction, but its exact performance was not necessarily fixed for all time. This suggests a careful description, reconfigurable mechanical sequencing. The phrase is less dramatic than ancient computer, but more accurate. Hero's device could carry out an ordered series of actions, and the builder could modify that order by changing the physical arrangement. It could not become a different kind of machine. A theatre designed to move figures could not suddenly calculate taxes or navigate a ship. Yet within its intended world, behavior could be revised. That is one meaning of programmability. Instructions are altered while much of the mechanism remains. Modern computers carry this principle enormously farther because software can be changed quickly and can represent countless tasks. Hero's theatre reveals a distant mechanical ancestor of the idea, not its completed form. Why did theatre encourage such complexity? A practical machine may repeat one operation and still be valuable. A pump raises water, a mill turns grain, a press applies force. Repetition is often the purpose. A story cannot survive on repetition alone. It needs order. One event must prepare another. A door opens before a figure appears. A sound arrives after a movement, not before it. Surprise depends upon delay. Resolution depends upon actions reaching a chosen end. To mechanize a story, the builder had to mechanize time. This is the first reveal. The theatre did not merely move objects through space. It controlled when each movement occurred, how long it lasted, and what followed. The sequence became a physical timeline. The second reveal is that storytelling may have demanded an early form of systems engineering. Several mechanisms had to share one performance without colliding, exhausting the power source, or destroying the illusion. The builder needed to think ahead through the entire chain. The audience experienced the result as drama. Behind the stage, it existed as controlled force. Still, the machine remained blind to failure. If a figure caught against the scenery, the later chords would not understand that the story had broken. The sequence would continue. True flexibility requires more than stored order. It requires information about what has actually happened. That limitation separates the ancient theatre from a modern robot. Modern systems may use sensors to confirm position, detect obstacles, or change plans. Hero's mechanism followed the prepared path whether the world cooperated or not. Yet its achievement remains extraordinary, because it demonstrates that an ancient builder could translate narrative into machinery. An imagined series of events became lengths, directions, releases, and rotations. The story was no longer only told, it was executed. The theatre also changes the larger investigation. Philo's servant showed conditional response. Ctesibius's regulator showed feedback-like correction. Hero's automata shows stored sequence. These are separate pieces of the robotic idea, appearing in different devices rather than one complete machine. Another piece waited in darkness beneath the sea. It did not animate servants or perform sacred drama. It used bronze gears to represent cycles of the sun, moon, calendar, and eclipses. Where Hero's theatre mechanized narrative time, the Antikythera mechanism mechanized cosmic time. Its corroded fragments would not be understood when first recovered. They looked too damaged, too unlikely, and too advanced for the assumptions surrounding them. The stage doors now close. The weight reaches the end of its descent. Far from Alexandria, beneath Mediterranean water, a different arrangement of bronze waits for its second discovery, in complete darkness. Near the small Greek island of Antikythera, the sea concealed a broken ship and its cargo for roughly 2,000 years. At the beginning of the 20th century, sponge divers descended into the water and found the remains. Statues emerged from the wreck, along with pottery, metal, and fragments of a world interrupted during travel. Among the recovered objects was a corroded mass of bronze and wood. It did not command attention like a marble figure. Its surface was dark, damaged, and fused by time. At first, it seemed to be only another ruined object from the ship. Then gear teeth appeared. That small detail changed the meaning of the fragments. Bronze gears belonged inside a mechanism, and the surviving pieces showed that the device had once contained many of them. The object no longer fit the comfortable image of ancient technology as limited to simple tools, pulleys, and decorative instruments. Its second discovery happened slowly. Each new scan did not merely reveal another part, it forced historians to enlarge what they believed ancient mechanics could achieve. The fragments entered museum collections, where scholars examined inscriptions and visible mechanical parts. Decades passed as researchers proposed different functions. Improved imaging methods later allowed them to look beneath the corroded surfaces. Hidden writing emerged. Internal relationships became clearer. The damaged mass began to reveal a machine of astonishing complexity. The first surprise was physical. Inside what looked like worthless corrosion lay a dense arrangement of precision gears. The second was historical. Nothing else from the ancient Mediterranean had survived in a form that offered such direct evidence of complex geared calculation from the same period. The machine appeared almost alone. Loneliness can make an artifact seem impossible. When no close relative survives, observers may assume the object was unique, experimental, or misunderstood. Yet survival is not the same as original rarity. Bronze was valuable. A broken mechanism could be dismantled and melted into coins, tools, vessels, or weapons. Wooden cases rotted, fine teeth corroded. A device that required maintenance might vanish within generations after its knowledge disappeared. The Antikythera mechanism survived partly because disaster removed it from ordinary cycles of reuse. The sea destroyed much of it, but the sea also saved it. That contradiction turns the wreck into a warning. Archaeology shows what happened to remain, not everything that once existed. One surviving machine cannot prove a large industry, but neither can its uniqueness prove that ancient craftsmen never made related devices. The object must therefore be treated with balance. It is not evidence of a hidden electrical civilization, and it does not show that ancient workshops mass-produced modern computers. It does prove that skilled makers could design and manufacture a compact system of interlocking bronze gears for a highly sophisticated purpose. The exact history of its creation remains uncertain. Its makers are unknown. Its workshop has not been recovered. Scholars continue to debate parts of its reconstruction. But the central fact is secure. This was a working mechanical instrument, not a decorative fantasy. Its presence changes how the written automata are judged. Hero's descriptions of coordinated devices can no longer be dismissed, simply because their complexity feels too modern. The mechanism from Antikythera demonstrates that ancient craftsmen could embody difficult relationships in carefully made moving parts. The gears were not intended to power a cart, weapon, or lifting machine. Their purpose was quieter and stranger. They transformed turns of a handle into displays of astronomical time. Within the corroded fragments, mathematics had become movement. Cycles observed in the heavens had been placed into ratios between bronze teeth. The wreck had not preserved a robot. It had preserved another missing piece of the same ancient dream, a machine capable of carrying knowledge through its own motion. To understand what the gears calculated, the documentary must now enter the device itself, passing from the ruined surface into a universe made of bronze. Imagine a wooden case held in the hands. On its exterior are displays and inscriptions. A handle or knob is turned. Inside, bronze wheels begin to move, each tooth pushing the next. The motion passes through a network of gears, and the sky itself seems to advance. The Antikythera mechanism was a hand-powered astronomical calculating device. Its surviving fragments show gear trains designed to represent calendar and celestial cycles. The machine could connect a chosen date with positions or patterns involving the sun, moon, and eclipses. It did not observe the sky directly. It embodied relationships that ancient astronomers had already studied. The basic principle begins with two gears. If one wheel has a different number of teeth from the wheel it drives, the second wheel turns at a different rate. One complete rotation can become a fraction of another. Combine several pairs, and a single input can produce multiple motions, each following its own cycle. The numbers are carried by metal. This is why the device is often called a mechanical computer. It processes a turning input according to fixed mathematical relationships and produces organized displays. The calculation is not performed with electronic signals. It is performed by the ratios between teeth. A gear cannot understand the moon. Yet if its size and tooth count have been chosen correctly, its motion can represent a lunar cycle. Another train can embody a longer period. A pointer can move across markings. A dial can show when a repeating astronomical event is expected. The first great reveal is that theory had become hardware. Knowledge once expressed through observation, number, and diagram had been translated into a machine that could be operated by hand. The second lies in the moon's uneven motion. The lunar cycle is not represented by a single perfectly uniform turn. Researchers have identified ingenious gearing that modeled variation, showing that the designers were not satisfied with a crude decorative display. They wanted mechanical motion to follow a more subtle astronomical pattern. Such precision required several kinds of skill at once. Someone had to understand the cycles. Someone had to select useful ratios. Someone had to lay out the gear trains so they could fit within a compact case. Craftsmen then had to cut many fine teeth, mount axles, reduce friction, and keep the moving parts aligned. The mechanism therefore implies more than one brilliant idea. It implies a technical environment in which mathematics and metalworking could meet. No complete instruction manual survives beside it. Corrosion has destroyed parts, and reconstructions remain subjects of debate. The documentary should not pretend that every display is known with absolute certainty. What survives is enough, however, to establish the device's extraordinary purpose and complexity. The machine also invites a dangerous leap. Because it is advanced, some may imagine that all ancient technology must have been equally advanced, hidden or lost. That conclusion goes beyond the evidence. One remarkable survivor expands the known boundary. It does not erase every difference between antiquity and the modern world. Its true significance is stronger without exaggeration. The Antikythera mechanism shows that ancient craftsmen could build dense, precise, multi-stage gearing capable of representing abstract knowledge. This ability belongs beside the hydraulic and pneumatic traditions of automata, even though the device itself was not a robot. Still, the theatre used those patterns to tell a prepared story. The astronomical mechanism used them to carry the heavens forward and backward through time. Turn the handle, and the sky obeys. Of course, the real sky does not change. The machine changes its model. This distinction is important. The device creates a controlled miniature world in which celestial cycles can be explored through movement. That act of modeling lies close to modern computation. A computer does not contain the weather, a distant planet, or a financial market. It contains representations governed by rules. The ancient mechanism did the same in a limited mechanical form. Its existence raises a final question. Could a machine this sophisticated truly have appeared without relatives, predecessors, teachers, failed designs, and specialized workshops? Only one example has survived. But one surviving example may be the remaining leaf of a mechanical forest that was cut down, melted, and forgotten. The Antikythera mechanism and Hero's automata do not belong to the same category. One calculated and displayed astronomical cycles. The others opened doors, poured liquids, produced sounds, or moved figures through prepared performances. Treating them as identical would blur their real achievements, yet they reveal complementary abilities within the ancient mechanical world. Antikythera shows precision gearing, compact assembly, and mathematical relationships embodied in bronze. Hero's devices show controlled energy, timed sequence, triggered response, and theatrical motion. Ctesibius's regulators show stability. Philo's servant shows physical interaction. No single machine contains every element, but the pieces no longer appear isolated. The surviving geared calculator makes the written automata easier to believe. A description of chords, axles, valves, and coordinated figures may sound fanciful when no complex ancient machine is visible. The corroded fragments from the sea demonstrate that craftsmen could construct mechanisms whose internal organization exceeded what later observers once expected. This does not prove every ancient design was built. A text may describe an ideal device, a teaching example, or a machine attempted only once. But the boundary of possibility has moved. Why, then, does Antikythera stand almost alone? The first answer is material. Bronze invited reuse. A device that failed, became outdated, or lost its owner could be dismantled. Its gears had value even when its purpose was forgotten. Melting erased the machine while preserving the metal. The second answer is fragility. Fine teeth could bend or corrode. Wooden frames could rot. Axles could seize. A mechanism required people who understood its maintenance. Once that knowledge disappeared, the object might become an expensive box of useless parts. The third answer is survival through copying. Literary works could continue as words even after their original papyrus decayed, provided later readers copied them. Mechanical objects had no such protection. Technical manuscripts also faced risk, because diagrams and specialized terms were difficult to preserve accurately. Unique survival, therefore, does not equal unique manufacture. At the same time, the opposite claim must be resisted. One artifact does not prove a hidden ancient industrial world filled with computers and robots. No evidence shows electrical networks, automated factories, or armies of mechanical servants. The lost family of machines, if it existed, was shaped by ancient materials, ancient economies, and ancient purposes. The honest possibility is narrower and more interesting. Specialized workshops may have produced a range of complex instruments for wealthy patrons, scholars, courts, temples, or navigators. Some may have been unique commissions, others may have belonged to traditions, whose examples were later recycled. The Antikythera mechanism is therefore both evidence and absence. It proves that extraordinary geared construction occurred. It also points toward missing predecessors, experiments, tools, and craftsmen required to make such an object possible. A mature mechanism rarely appears from nothing. Before the final device, there are failed versions, simpler models, learned techniques, and hands trained by earlier work. None of those relatives has survived clearly enough to reconstruct the workshop tradition. That missing background deepens the mystery without requiring fantasy. It also changes the question. The puzzle is no longer simply whether the Greeks could build sophisticated machines. They could. The harder question is why their knowledge did not produce an ancient age of factories, engines, and widespread robotic labor. Modern observers often imagine invention as a spark that must ignite progress. If steam spins a sphere, why does it not power industry? If gears calculate the heavens, why do they not enter every workshop? If automata can perform sequences, why do they remain spectacles? The answer lies beyond any single device. Technology grows only when materials, energy, labor, investment, demand, and institutions support it. An invention can be brilliant and still remain rare. The bronze universe from the sea now stops turning. The next chapter examines the world around it and asks whether the ancient machines truly failed, or whether they succeeded perfectly at purposes modern people have forgotten how to value. A single invention does not create an industrial age. The idea seems obvious, yet history is often told as if one brilliant machine should automatically produce the next. Hero demonstrates steam-driven rotation, so why does a factory not appear? Greek craftsmen build precise gears, so why are clocks not placed in every town? Automatic theaters perform sequences, so why do mechanical workers not enter farms and mines? The missing step is not one discovery, it is an entire supporting world. A useful industrial machine requires materials that can survive repeated stress. Its parts must be produced with enough consistency that repairs are possible. It needs an affordable source of energy, people trained to maintain it, owners willing to invest, and a reason strong enough to replace older methods. Roads, workshops, markets, and institutions must carry the invention beyond the place where it first succeeds. Ancient automata often existed in different conditions. They could be commissioned as demonstrations, sacred effects, scientific instruments, or signs of elite power. A court might reward uniqueness rather than standardization. The stranger and rarer the device, the greater its value as a marvel. A machine made for astonishment does not need to become cheap enough for every household. Hero's Aeolipile illustrates the gap between principle and industry. Heated water produces steam. The steam escapes through bent tubes and causes a sphere to rotate. The device demonstrates that heat can create motion. But rotation alone is not an efficient engine. To power sustained work, a system needs strong boilers, reliable seals, controlled pressure, useful transmission, and an economic setting where fuel and machinery can compete with existing labor. A spinning sphere proves a physical effect. It does not solve all the problems required to drive a mill, pump a mine, or move a ship. It is tempting to explain the absence of ancient industry with one word: slavery. Coerced labor may have reduced incentives for labor-saving machinery in some places and tasks, but the ancient economy was not uniform, and machines that reduced labor did exist. Water mills, lifting devices, presses, and pumps show that practical mechanization was not unthinkable. No single cause is sufficient. Progress requires alignment, and ancient brilliance often appeared where that alignment was temporary, narrow, expensive, or tied to one powerful patron alone. Fuel mattered. Metallurgy mattered. Precision production mattered. Political stability, investment, transport, and demand mattered. So did the social purpose assigned to technical knowledge. A clever mechanism might be admired as philosophy made visible rather than developed as a product for widespread work. This leads to the first reveal. The automata may not have failed. They may have succeeded at the goals their patrons valued. A temple door created awe. A mechanical theater displayed skill. An astronomical calculator organized celestial knowledge. A serving figure transformed a banquet into wonder. Modern observers judge technology by scale, productivity, and economic growth. Ancient patrons may have judged the same object by rarity, beauty, intellectual elegance, ritual force, or political meaning. The second reveal is that technological progress is not a ladder. A society can understand a principle without combining it with every other principle needed for industrial transformation. Knowledge can remain local. Workshops can vanish. An expensive masterpiece can have no practical descendant. The ancient world did not stand one forgotten invention away from modern robotics. Too many supporting systems were absent or differently organized, yet this does not make its machines failures. It places them inside their own world. The question now changes from why the Greeks did not become modern to how their mechanical knowledge disappeared so thoroughly. A stone temple can remain for centuries after its builders are forgotten. A delicate machine has a different fate. Its cord rots, its wood splits, its bronze waits for the furnace. The next part of the mystery begins when a marvelous device stops working and becomes more valuable as raw material than as memory. Imagine an ancient automaton after its final performance. The cord has begun to fray. A wooden support has warped. One valve leaks, and the person who once knew how to adjust it is gone. The machine still looks impressive, but its movements are uncertain. Repair requires time, skill, and materials. Then someone notices the bronze. The metal in a gear, vessel, pipe, or decorative figure remains valuable even when the mechanism no longer works. It can be melted and given another life as a tool, coin, weapon, fitting, or household object. The machine disappears, but its substance survives in a form that carries no memory of the original design. Wood follows a quieter path. It splits, rots, burns, or is reused. Leather hardens. Rope becomes dust. Iron corrodes. Small parts scatter. Within generations, a device that once seemed miraculous may leave almost nothing that an archaeologist can identify. Complex machines are therefore strangely vulnerable. A stone wall can remain after its purpose is forgotten. A bronze statue may survive because its form continues to be valued. An automaton depends upon relationships between parts. Remove the cord, melt the valve, or lose the axle, and the meaning of the surviving pieces becomes difficult to see. The same fragility affects written instructions. A manuscript does not survive merely because it was important. Someone must copy it before the material decays. Then another person must copy that copy. Each generation must believe the text is worth the labor. Sometimes survival depended upon one unknown copyist choosing machinery over an easier book. Poetry, law, religion, and widely taught philosophy often had communities committed to preservation. A difficult technical work filled with unusual terms and diagrams could be easier to neglect. Even when copied, it could change. A line placed incorrectly in a drawing might connect the wrong vessels. A missing label could make a valve impossible to understand. A translator might have no exact word for a specialized part. Measurements could be altered. A scribe could simplify an image that appeared decorative but actually contained the machine's logic. Technical knowledge is often less tolerant of error than narrative. A damaged story can still move a reader. A damaged mechanism may simply fail. Hero of Alexandria is himself partly hidden by this process. His personal life remains uncertain. What survives most strongly is a collection of technical works associated with his name, transmitted through manuscripts, translations, editions, and scholarly reconstruction. The person becomes faint, while the machines remain as textual shadows. The phrase textual shadow is appropriate because a description is not the object. It cannot preserve the exact sound of gears, the friction in a pivot, the smell of heated wood, or the patience required to seal a leaking joint. Modern builders can reconstruct devices, but they inevitably make choices where the text is unclear. Those choices do not make reconstruction worthless. They reveal which readings are possible. A working model can show that an arrangement has mechanical sense. A failed model may expose a copying error, a missing detail, or a modern misunderstanding. Still, only a fraction of ancient mechanical knowledge may have reached the present. What survives is not necessarily what was most advanced. It is what escaped fire, reuse, neglect, war, damp, insects, and changing taste. This is the first reveal. Sophisticated technology can leave a weaker archaeological trace than monumental architecture. Its value encourages recycling, and its complexity makes broken remains difficult to interpret. The second is more unsettling. History may remember ancient engineers through the devices later readers happen to copy, not through the full range of machines they actually knew. That possibility must remain restrained. Absence cannot be filled with imagined robots. Lost evidence permits questions, not unlimited claims. Yet the surviving fragments are enough to show that the record is incomplete. The tradition did not vanish in a single night. Pieces moved into other languages and cultures. Greek works were translated, studied, corrected, and expanded by later engineers. The mechanical path continued, though it no longer followed one city or one people. The broken automaton enters the furnace. The manuscript enters a translator's hands. One form disappears as another carries part of its design into the future. The history of machinery did not fall into darkness when the ancient Mediterranean changed. Knowledge moved, but movement transformed it. Greek technical writings passed through new languages, new courts, and new workshops. Scholars in the medieval Islamic world translated and studied works connected with mechanics, mathematics, astronomy, and pneumatics. They did not simply place old texts on shelves. They tested ideas, corrected problems, combined traditions, and built new devices for different patrons and purposes. This distinction matters. Transmission is not passive preservation. A copied mechanism enters another material world. Craftsmen have different tools. Rulers desire different displays. Religious settings, palaces, gardens, clocks, and water systems create new questions. An inherited valve or siphon becomes part of another invention. The 9th century Banu Musa described ingenious devices using vessels, pressure, floats, valves, and automatic control. Their work belongs to its own intellectual setting, yet it also shows how older pneumatic principles could be expanded into increasingly subtle systems. Centuries later, Al-Jazari documented remarkable clocks, pumps, fountains, and automata, whose complexity and artistry deserve recognition beyond any role as a bridge to Europe. They created. At the same time, their work helped preserve a larger mechanical conversation. Some Greek texts survived because they were translated beyond the Greek-speaking world. Ideas that might have vanished in one region continued elsewhere, altered by every hand that used them. The first reveal is that the road from Hero to modern automation is not a straight European line. It crosses cultures, languages, religions, and political worlds. At several points, knowledge survives because another society finds value in it. The second is that rediscovery often hides earlier continuity. Renaissance and early modern readers became fascinated with hydraulics, fountains, theatrical machinery, and ancient technical texts. Printed editions made works connected with Hero available to wider audiences. Yet those readers were not awakening ideas that had slept untouched for 1,000 years. They were entering a tradition that had traveled and changed. Mechanical history resembles a river dividing into channels. One branch carries astronomical instruments, another carries clocks, another carries water control, spectacle, or industrial machinery. Branches disappear underground, reappear, or join streams that developed independently. Modern robotics emerged much later from many of these channels. Precision gears, improved metallurgy, steam and electrical power, formal control theory, electronic sensing, computing, and software all became necessary. No ancient text contained the completed roadmap. This is why the beginning of robotics cannot honestly belong to one inventor or civilization. Ancient Greek automata contributed early examples of automatic movement and sequence. Engineers of the Islamic world developed sophisticated control devices and preserved important knowledge. European mechanical traditions expanded clocks, engines, and industrial systems. Contributions from many regions shaped materials, mathematics, instruments, and computation. The desire for a single birthplace is understandable. A clear origin makes history easy to tell. But machinery rarely begins at one point. It grows whenever people learn to make force more reliable, instructions more precise, and objects more responsive. The long journey also changes the meaning of lost knowledge. Some ideas were truly forgotten. Others were absorbed so deeply into later craft that their origins became difficult to see. A valve design may survive even when the name of its earliest maker does not. A mechanical principle can travel without carrying a passport. After 2,000 years, the pieces can finally be placed beside a modern robot. The comparison will not reveal an unbroken machine lineage. It will reveal recurring problems: how to sense a condition, regulate change, store a sequence, calculate a relationship, and produce controlled movement. The final chapter returns to the bold claim that began the investigation. Did robotics begin in ancient Greece? The answer will be neither the simple yes promised by sensational history, nor the simple no offered by those who see only electronics. It lies in the space between origin and ancestry, where ancient machines still move beneath the surfaces of modern ones. Place a robot on one side of the room and the surviving ancient machines on the other. The distance between them seems complete. The robot may have cameras, electric motors, processors, software, and joints that move with precision. The ancient devices are made from water, air, bronze, wood, rope, and falling weights. Yet when the machine is separated into functions, familiar pieces begin to appear. A robot needs energy. Ancient automata also required a source of power: heat beneath an altar, water held above a lower level, compressed air, or a suspended weight. A robot needs to receive information. Philo's servant accepted the weight of a cup as an input. Ctesibius's float followed the level of water. These devices did not see or understand, but physical conditions entered their mechanisms and changed what happened next. A robot needs control. Valves, levers, pipe dimensions, knots, and pegs restricted force and determined order. Their rules were fixed in material rather than software. A robot needs actuation, the ability to create physical movement. Ancient cords turned axles. Pressure moved liquid. Weights opened doors. Figures rotated, hands descended, and pointers crossed marked surfaces. A robot may use feedback to maintain stability or correct an action. Ctesibius's regulating float offers a feedback-like arrangement in which changing water level influences the incoming supply. A robot may follow stored instructions. Hero's theatre preserved a sequence in the winding and routing of cords. Alter the arrangement, and the order or direction of actions could change. A robot may calculate. The Antikythera mechanism embodied astronomical relationships in gear ratios, transforming a turning input into coordinated displays of cycles. No single ancient machine combines all these abilities. That is the essential limit. Philo's servant reacts, but it cannot reason. Hero's theatre follows a sequence, but it cannot notice failure and revise the performance. The float corrects a level, but it has no general goal beyond the relationship built into its linkage. Antikythera calculates fixed cycles, but it does not control a moving body. The modern robot unites functions that antiquity developed separately. Electronic sensors can measure many conditions. A computer can compare them with stored goals. Software can choose between possible responses. Motors can act, and feedback can report whether the action succeeded. Some systems can plan, recognize, or learn. Ancient automata had no such flexible center. Their intelligence lived entirely in the builder's arrangement. Once completed, the machine could only follow the narrow world prepared for it. This does not weaken their importance. It reveals how robotics actually emerged. There was no single morning when humanity invented the complete robot. Different generations solved different problems. One learned to regulate flow. Another learned to transform pressure into action. Another learned to store order in physical sequence. Another learned to embody calculation in moving parts. Later ages added reliable engines, precision manufacture, electricity, formal control, electronics, and computation. The history of robotics is therefore less like the birth of one object and more like the assembly of a body across centuries. Ancient Greek engineers contributed several early bones. The image is not a claim of direct descent. A modern robotic arm was not copied from Hero's theatre, and a computer controller is not a bronze float. The relationship is conceptual. Similar problems return whenever humans attempt to make matter perform a task without continuous guidance. That is the evidence hidden beneath the title. The Greeks did not possess modern robotics as a field, an industry, or a complete technology, but they demonstrated that automatic behavior could be divided into mechanisms: input, regulation, sequence, calculation, and motion. The final question is no longer whether an ancient automaton should be placed in a modern factory. It is whether the roots of robotic behavior can begin long before the word robot existed. The next section gives the verdict, separating the bold promise of the title from the deeper claim the evidence can truly support. The title makes a bold promise. Ancient Greek automatons prove that modern robotics began thousands of years ago. Taken literally, that statement goes too far. Modern robotics is not simply the art of making an object move. It depends upon technologies and institutions the ancient world did not possess. Electric power drives precise motors. Electronic sensors translate light, sound, heat, pressure, and distance into signals. Computers process those signals. Software selects actions. Modern factories produce standardized components. Research fields develop theories of control, planning, perception, and artificial intelligence. That connected system belongs mainly to the modern age. Ancient Greek engineers did not build electronic robots, intelligent androids, or general-purpose machines capable of learning new tasks. No evidence supports hidden laboratories filled with metal workers that could think. There was no uninterrupted robotic industry stretching from Alexandria into the present. If began means the birth of modern robotics as a recognized scientific and industrial field, the answer is no. But history becomes more revealing when began is understood as conceptual ancestry. Ancient devices show that engineers could create movement triggered by an outside condition. A coin could release water. A cup could begin a serving sequence. Fire could open doors. They show that a machine could regulate change. A float could respond to water level and influence the incoming flow. They show that instructions could be stored physically. Chords, pegs, and drums could preserve the order of a theatrical performance. They show that abstract relationships could be embodied in mechanisms. Bronze gears could calculate astronomical cycles through motion. These are not modern robots, but they are foundational ideas within the larger history of automation. The first final twist is that the Greeks did not need a word for robotics to contribute to its development. People often solve parts of a problem long before anyone recognizes those parts as belonging to one future field. A valve maker, clock designer, theatrical engineer, and astronomical instrument builder may all work on different tasks, while advancing principles later joined inside one machine. The second twist is that ancient technology appears simple, partly because its materials are familiar. Rope, water, and wood do not look intelligent. Yet a rope can store a sequence through its winding. A float can carry information through position. A valve can enforce a condition. A gear ratio can embody a mathematical relationship. Electronics make these functions faster, smaller, and more flexible. They do not create the desire for organized behavior from nothing. The strongest verdict, therefore, lies between celebration and dismissal. Ancient Greek automata were not modern robots. They were early experiments in making physical systems act according to prepared rules. They belong to the deep prehistory of robotics. A builder wants a door to open after a fire is lit. He arranges vessels, pipes, water, cords, and counterweights until heat produces that result. A builder wants a figure to serve a drink after a cup is offered. He arranges balance, reservoirs, and passages until weight produces that result. A builder wants a story to unfold without visible actors. He arranges chords and a descending weight until time itself produces the sequence. In every case, the machine carries a human decision forward after the human hand has withdrawn. That is the ancient contribution. Matter is given a task, constrained by a rule, supplied with energy, and released. The machine does not understand. It does not need to. Its behavior has been organized before the moment of action. So did robotics begin in ancient Greece? Not as a modern discipline, and not in Greece alone. Its roots spread through many cultures and periods. But several roots reached deep into the workshops of the ancient Mediterranean. The title is therefore best understood as a doorway, not a verdict. Behind it lies something more credible than a lost robotic civilization, and more surprising than a collection of clever toys. It lies in the recognition that organized machine behavior is older than electricity, older than software, and older than the word used to describe it. The final section leaves definitions behind. It returns to the human dream that first placed moving servants in the forge of Hephaestus, and still places intelligent machines in laboratories today. A modern robotic arm moves beneath white factory light. It turns, pauses, lowers a tool, and repeats the same action with tireless precision. Its motors are electric. Its instructions are digital. Sensors confirm its position before the next movement begins. Now the scene begins to travel backward. The electronic controller becomes a rotating drum. The software sequence becomes a cord wound along a prepared path. The theater fades into a smaller figure holding a jug. A cup enters Philo's servant's hand. The hand lowers. Hidden passages open. Wine and water flow according to a rule the machine cannot understand. The servant becomes a simple float resting on water. The level rises, and the float rises with it. A lever turns. A valve narrows. The system protects its rhythm without thought. The vessel disappears beneath the temple floor. Fire warms trapped air. Water moves into a hanging container. Ropes tighten. Great doors open while the crowd waits above. The stone temple dissolves into the coastline of mythic Crete. Talos circles the island in bronze, following a command older than any surviving machine. Farther back, inside the forge of Hephaestus, artificial attendants stand beside the god who made them. The mechanisms change, but the dream remains recognizable. Human beings have always wanted objects that could carry burdens, serve guests, guard boundaries, measure time, perform stories, calculate nature, and act in their place. Every age built that dream from the materials it understood. Myth used divine craft. Alexandria used air, water, balance, and weight. Later workshops used springs, clocks, engines, electricity, electronics, and code. There is no single blueprint connecting every stage. Hero did not design the modern factory robot. The Antikythera maker did not foresee software. The line between ancient automata and present machines is broken, branching, and shared across many cultures. Yet the recurring desire matters. Again and again, people attempt to turn intention into mechanism. They imagine an action, divide it into causes, and arrange matter so the action continues after their hands withdraw. That is why the ancient devices still feel strangely alive. Their materials are simple, but their behavior carries purpose. A door waits for heat. A servant waits for weight. A theater waits for release. The waiting belongs to the design, not the object. Yet the distinction becomes difficult to feel while the action unfolds. The deepest mystery is therefore not whether the machine has a soul. It is why human observers so readily place one inside organized movement. When an action matches the moment, intention is imagined. The temple answers. The servant notices. The bronze guardian chooses. The machine becomes a character because its response arrives where a response belongs. Modern robotics has made that illusion more powerful. Machines can now detect faces, interpret speech, map unfamiliar rooms, and adjust their behavior. The distance between appearance and understanding has narrowed, but it has not disappeared. People still ask how much the machine truly knows, and how much meaning they have supplied themselves. Ancient automata stand at the beginning of that question. They show the minimum required to make matter seem purposeful. A trigger, a rule, energy, and a visible result. The journey ends beneath the temple floor. The fire above has weakened. Air cools inside the sealed vessel. Water returns through the pipe. The hanging container grows light. The counterweight descends, and the doors begin to close. The crowd sees the god withdraw. The engineer, if he is present, hears something else. The soft return of a system to its starting state. Ropes loosen. Water settles. Stone meets stone. The machine becomes still, but the idea inside it does not disappear. The Greeks did not build the robots of the modern world. They built something earlier, the possibility that a machine could be given a task, released, and trusted to finish it alone. Beyond the closed doors, that possibility waits for another age to open it.